Not a lot.
I don't know.
Basically 0.
It's special.
I have no idea. I have no idea what that even is.
I really don't know much, actually. Not much.
It's important.
I'm not a science major.
Never took physics, so.
Einstein, right? He was the one that came up with it.
I think that's the E equals MC squared thing, maybe?
I know that it's like E equals MC squared, I think. And I really only know that because Mariah Carey had an album that was titled that.
No, I don't really know anything. All I know about is Einstein parody accounts on Twitter. You should follow me on Twitter.
And it has to do with like time travel and Interstellar. Totally.
When it first came out, it was pretty big, but like it really had big implications for later events in history.
I have no idea what it is. Don't know any of that stuff.
Or it's something about gravity can warp time, space, etc. That's all I got.
I wish I knew more. I should know this because I'm a physics student, but I didn't do terribly well at this part.
It's a real effect. There have been a number of experimental measurements to demonstrate that this idea that space and time are coupled inextricably.
Einstein's theory of special relativity states that when you're traveling very fast at a significant percentage of light speed, time is slower for you than someone else.
So, generally speaking, it's known that we in our world will go about the world in like a constant time and space, and when we walk 2 meters, we're walking 2 meters. But for the very, very fast and the very, very small, those constants start to break down.
Qualitatively, if you're traveling at a certain velocity, with respect to something else, you'll experience either length contraction or time dilation. And in this case, what we observe is an actual sort of change in how time is perceived by relative observers, or how length is perceived by relative observers.
So, for example, if you had a train moving at like half the speed of light, and on that train you had somebody running also at half the speed of light, that person's total velocity would not actually be the speed of light. It would be some fraction of the speed of light, because very, very fast speeds start to add up at certain proportions of their actual total velocity. And that basically accounts for the fact that there's a cosmic speed limit, c, or 3 times 10 to the 8th meters per second, which can't be surpassed.
An inertial reference frame is when you aren't accelerating, so when people are sitting still, or if you're traveling at a constant velocity. Your calculations are similar to sitting on Earth.
And you arrive at some amazing reality that changed the shape of the scientific world forever.
Relativity is not a 21st century concept. Galileo believed all speeds and positions are relative, and that all reference frames are equally valid. Imagine you are on a ship moving at a constant speed, sitting in the bird's nest on top of the sail, and you drop a ball. Because your reference frame moves at the same velocity as the ball appears to fall straight down. Now consider this perspective of someone standing stationary on the shore. His reference frame has no velocity relative to the ship and the ball. Because the velocity of these two reference frames are not equal, the person on the shore sees the motion of the ball differently. To him, the ball appears to move downwards in a curved arc, rather than in a straight line. Which reference frame is correct? According to Galilean relativity, both your reference frame from atop the sail and the reference frame from the shore are equally valid. Because all motion is relative, there is no preferred reference frame. Galileo's theory of relativity was dependent on inertial reference frames, which are reference frames that are not accelerating in motion. You are either at rest, like the viewer on the shore, or moving with a constant speed, like the man on the boat.
Through the context of inertial reference frames, Einstein's special theory of relativity emerges. This theory describes relative motion between two respective objects moving in a straight line at constant speeds comparative to each other. However, this theory indicates the respective principles of relativity and speed of light. These confirm that basic physical laws and the speed of light relative to all observers are both continuous. More specifically, Einstein's theory of special relativity asserts that the fundamental laws are consistent for all stationary spectators. Therefore, the speed of light in a vacuum is also constant, regardless of the relative speed of the observer. This theory of special relativity inherently linked space and time, which signifies a four-dimensional element to the universe, and creates a space-time continuum. This notion establishes why the observations of numerous onlookers moving at different speeds will differ vastly. A major difference between Galilean relativity and Einstein's special theory of relativity can be found in the time ordering of events. While Galilean relativity states that all events occur in a specific order, Einstein's special theory of relativity asserts that the time ordering of events is not definite, meaning that to different observers and different inertial reference frames, it may appear that the events happen in different orders. Imagine a car moving at the speed of light. Now imagine that you are standing on the sidewalk watching the car move along the road. When the car is exactly halfway past you so that there is an equal amount of the car on either side of you, imagine that both the front and back of the vehicle are struck by lightning. Because you are equidistant from these 2 points, and because the speed of light is a constant, the lightning strikes will appear to occur simultaneously from your reference frame. Now imagine that you are sitting in the middle of the car, so that there is an equal amount of car on either side of you. Again, imagine that the front and back of the car are struck by lightning. Although you are still equidistant from the 2 strike points, the strike on the front of the car will appear to occur before the strike on the back of the car. This variation is accounted for by the velocity of reference from inside the car. Because you are moving towards the strike point on the front of the vehicle, the light it emits will reach your eyes before the light that is emitted from the strike point on the back of the vehicle. Much like in Galilean relativity, there is no preferred reference frame, so both the observer standing on the sidewalk and the observer inside the car are equally correct. In Einstein's special theory of relativity, we are shown that the time ordering of events is not definite and changes based on the frame of observation.
Another defining characteristic of Einstein's special theory of relativity is length contraction. Because observers in separate reference frames will not agree on the simultaneity of events, objects traveling at or near the speed of light will begin to contract. Imagine 2 sets of mirrors, each reflecting a beam of light. Now imagine that one set is stationary, while the other is moving at a velocity close to the speed of light. From a stationary reference frame, the light beam bouncing between the stationary mirrors will appear to have a constant length. However, from a reference frame that is moving at approximately the speed of light, the light beam will appear to contract. Because the mirrors are in motion, light will actually be traveling in a V pattern, increasing the distance light has to travel. As you may remember, the equation for speed is distance divided by time. If the distance that light has to travel increases, then time must also increase to maintain a constant speed, such as the speed of light. If this were not the case, the ratio of distance to time would be altered, changing the speed. However, while time can dilate, it cannot completely make up for the increase in distance. In order to maintain a constant ratio, length must also contract. Therefore, the mirrors will appear to move closer together. In this way, the ratio between distance and time is kept the same, and the speed of light remains a constant.